Hello everyone, I'm Mu-Rong Wang from KTH, and it is my honor to be here in Ekman, Dagna to present my research work on spinning the world's strongest bio-based filament. And it is a scale from lab scale into the industrial in this presentation. So, as the society is pursuing to sustainable world, we want to replace the plastic materials with more natural-based sources. And that's why with our material and our techniques, we're able to spin the world's strongest bio-based filament apart from other natural sources. And all this scientific background goes back to the composition of wood, which cellulose, hemicellulose, and lignin are the three main components. Because of the strong mechanical properties of cellulose, we want to spin it into strong filaments. And with our modifications, which we choose as the tempo-mediated oxidation, we get a negative charge on the C6 site. And by passing it through the homogenizers, we're able to get CNFs, the cellulose nanofibrils, out from cellulose. We then inject these CNF dispersions into our flow focusing channel as shown in the illustration here. So with the two sheath flow coming from the site, we're able to first align our fibrils in the flow and then fix the direction of them. So the purpose of the first sheath flow is that it can kind of detach our CNF dispersions from our channel wall and align our fibrils in the flow. However, after the downstream of the flow, the Brownian motion of these fibrils will then de-align these fibrils again in the downstream. That's why we need the second sheath flow coming later. And what this second sheath flow does is that it carries cations, which are the counter ions compared to the CNFs. This will then reduce the electronic repulsion force between the fibrils and fix the direction of them in the flow. And the resulting filaments have really strong mechanical properties. And if we can further apply this into different fields, as in textile industry, in biomaterial, or even in electronic devices, it is really a perfect way to replace plastic materials with our filaments. However, to do so, we need to make this whole spinning process upscalable without hand-picking our samples. That's why we start to separate our spinning process into three different parts. With different treatment and also the characterizing method, we can track the quality of our raw material and also our final product. So the first thing that we should do is to remove the impurities and aggregates inside our CNF dispersions, as shown here. And these aggregates could become a weak point or impurities in our filaments. That's why we want to remove them with cleaning process. So what we do is that we first ultrasonicate our CNF dispersions following up concentration and centrifugation. That's how we remove this aggregate from the dispersion. And we can up-concentrate again the CNF dispersion to a desired concentration. After doing so, we want to understand how this CNF network will behave dynamically in a flow. And that's why we start to put our channels in between two cross-polarized filters and track the intensity and the alignment of these fibrils. So in the video coming soon, we'll see a flow in a channel with higher intensities in the core. And after 5 seconds of continuous flow, we stop the flow and observe a decay in the intensity. And this decay comes from the relaxation or the disassembly of the network. It will further affect how continuously we can spin out these filaments. And the faster it decays, the faster our network disassembles. So it is a way that we can quantify this disassembly or even understand if we can continuously spin our filaments out from the flow or not. And once we get wet filament out from our channel, the drying time comes into play. So we have tested that by increasing our drying temperature, we're able to speed up this whole drying process without any degradation of our cellulose. And in the FTIR spectrum showing now, it is a characterizing method which gives us a certain absorption peak of certain boundings. And under the peaks under this area is mainly from cellulose, and the peak here mainly comes from absorbed water. This is how we characterize which kind of structure do we have as in the sample. And as drying time passes by, the contribution of cellulose increases and that from the absorbed water decreases. This is how we interpret this spectrum, as we can indeed speed up this drying process without changing the structure of our cellulose. And also from the environmental SEM image, we see that even though we have a slight change in the dimensions of our filaments, but the alignment and the packings of the fibrils in the filaments still remains when we dry it under a higher temperature. So by combining these three different treatment and characterizing methods, including cleaning CNF dispersions, understanding the relaxation and the disassembly of the network in the flow, and changing the temperature in the final step, we get to continuously spin out our filaments from our flow focusing channel. And indeed, we make it to optimize our parameters by this characterizing method and upscale the production of our filaments. And this is the idea of my research work of spinning the world's strongest bio-based filament. Thank you for your attention.